Okay, so this week in lab, what we're going to do is learn how to use Rcmdr to conduct two-sample hypothesis tests. Actually, I should write this as two-sample hypothesis tests and construct two-sample intervals. So the topic here is going to be two-sample inference. Okay, so in two-sample inference, we wish to make a statement about mu1 minus mu2. Okay, so this is our goal. Okay, so there's two ways that we can do this. Two ways to make said statement. One is a hypothesis test, and two is a confidence interval. Okay. All right, now, in each of these situations, there's going to be two distinctions that we have to make. Okay, so there's either independent samples or we have dependent or paired samples. Okay, and this is going to be consistent for both the interval and the hypothesis test. All right, now the structure of these procedures is actually going to be exactly the same as we talked about before. So the assumptions are going to be 1 SRS, 2 normality, and 3 sigma known. Okay, and that's going to be the same for both procedures. So in that sense, everything is basically identical. And then in terms of the actual process, our steps are going to be the same as well. So the hypothesis test, we can write it as having 6 steps. And our confidence interval, we can write it as having 3 steps. Okay. So on the first step, we have H naught versus HA. On the second step, we have alpha. On the third step, we have our test statistic. On the fourth step, we have the critical value or the p-value. On our fifth step, we have decision. And on our sixth step, we have conclusion. On the first step of the interval, we have the critical value. Then we have this confidence interval construction, and then we have conclusion. But the main difference is what we have to distinguish between in this case is whether or not the data is independent or the data is dependent. And what we're going to do in lab today is we're going to learn how to conduct hypothesis tests and confidence intervals in both situations. So for the independent sample tests and for the dependent sample tests. And in doing that, what we will also see are examples of what this data looks like in each of the different situations. So what independent data looks like for the hypothesis test and what dependent data looks like for the hypothesis test. And that will be the same as for the confidence interval. Okay. Does anyone have any questions before I turn it over to the Rcmdr stuff? All right. All right, so as per usual, what we'll do is I'll work through illustrations using Rcmdr. We'll bounce around those demo questions. We're going to need a few different data sets in order to work through this. I'll let you know what the data sets are slightly before I get started in case you need to download them. All right, so stop sharing screen. Yeah. Okay, I will start sharing screen. Yeah. Okay. All right, so we're going to start with, here's our demo question sheet. Okay, we are going to start with question number 24 on the demo questions. We're going to work a little bit out of order today because the tests are in a slightly different order than what we saw before. Okay, so question 24. Here's 18. 23 is right here. Yeah, yep. Okay, and then question 24. Okay, so, oh wait, sorry, not 24, 26. Sorry, I want to do 26. So we're going to start with question 26. Okay, so in question 26, we're working with the data file hours, home, work, gender. So this is going to be the data that we're utilizing in this particular question. Where's my chat box there? There it is. Okay. So we're going to start by opening up Rcmdr. So here's R. Here's my Rcmdr screen. Okay, so we have to load the data set. So we're going to go data, import data from Excel file. This is going to be our hours data. All right. So we will have Dropbox for me, McEwen, lecture material, fall, S151, lab data, hours, homework done. All right. Okay, so let's take a look at this data set. Come here. Oh, there we go. Okay, so this is a fairly large data set. So we have so the way the data set has been split up, in the first column, we have the gender. In the second column, we have the hours, the number of hours of home week the students do per classroom hour is recorded. Okay, so for example, here, the first observation is a female student or a student that identifies as female, and they perform 1 hour of homework per classroom hour. The second student is a student that identifies as being female and performs 3 hours of homework per classroom hour. The 36th observation is a student that identifies as male and performs 4 hours of homework per classroom hour. Now, in the question, we are asked to test at the 5% significance level whether there is significant evidence that the amount of homework done on average by female identifying students differs from the amount of homework done on average by male identifying students. Okay, so we want to conduct a hypothesis test at the 5% significance level to determine if there is significant evidence of a difference between the mean of the students identifying as male and the mean of the students identifying as female where the variable is number of hours of homework done per classroom hour. Now, the first thing that we have to consider, is this an independent test or a dependent test? Well, in the question, it actually says 2 independent samples of students, right? So that would be our first hint that it's an independent test. But if we didn't have that information, we would be able to determine that this is an independent test because because we're comparing 2 different samples of students. Right? Sorry, I just needed to check something there. So what I mean by that is you have a group of students that identify as male and you have a group of students that identify as female. These are independent samples. So the students in the group that identify as female are not related to, in the context of the variable, the students in the data set that identify as male. So we have 2 separate groups of students that have that are unrelated to one another. So basically, the students that identify as male have no influence on the students that identify as female in terms of, well, we assume they have no influence in terms of the number of hours of homework they do per classroom hour. So that is part of the rationale why we consider them to be independent. All right, so in 26, in part A, we're starting off with an assumption check. So fully and completely state the 3 assumptions that must be met in order to perform a 2-sample T confidence interval test for the mean of the number of hours of homework done by the males versus the mean of the number of hours of homework done by the females. We're also asked to create side-by-side frequency histograms for this data set. And the rationale for the histograms would be to check the normality assumption visually, though to be honest, the best way that we could actually check this normality assumption would be via the normal probability plots for each group. But we will work with the histograms for now, as this is what the question's asking for, and it'll be a refresher of how to do these things in R. Okay, so first off, the assumptions of the test. So here, our first assumption is that we have simple random samples in each group of students. The second assumption, actually let's write it as independent, simple random samples in each group of students. The second assumption is that the samples come from normally distributed populations. And then we could also write the third example as being the population standard deviations are known. Okay, so to create the side-by-side histograms, we go into Rcmdr and we select graphs, histogram. Okay, and then we will pick the first variable, which is HH per class hour. So the reason that we're using this variable right now is because in the options, because in the plot by groups, we're going to select gender. So that first column of data, we're going to use that to build the graph because we have the variable in the second column showing us which observations identify as female and which identify as male. When we go to perform the test later on, we'll be using the second or the third and the fourth columns because we need to use the separated columns in order to conduct the test. So we're going to group by gender. So we have HH per class hour, plot by gender, and then in our options, we can set our graph titles. So side by side histograms of, I'll just write, number of hours of homework. Right, and then our x-axis label will be the variable name, which is number of hours of homework per classroom hour. All right, we can click OK. And then you can see that what pops up here is the following chart. All right, and then this is what we can insert into Rcmdr. So if we go into our Rcmdr list, you can see that this was actually already inserted for us. So I'll just bring that back here. And I'm just going to scale this down so that we can get it onto one slide. Okay. Okay, so those are the assumptions, at least as I teach them. And we have our side-by-side histogram here. In part B, we're asked, highlight or circle correct answers below. The shape of the histogram of sample data for females looks, okay, so if we go back up, we consider the first histogram. What shape do we think this has? I would say that this is skewed left very slightly, though in the solution guide, it's written as normal. I guess you could get away here with calling this symmetric. This first histogram shown above. I think it's a little bit less skewed because of this downward trend here, but we'll say that it's fairly symmetric, so we'll go with normal. But the second one is certainly skewed right. So you can see the mode kind of sits over 1 and point, or the modes are kind of around 1 and 2 here, and then we have a very sharp decline down to about 5. So this is certainly a skewed right data set. The shape of the sampling distribution of the test statistic is, so in this case, we are told, okay, so in each group, no, uniform is a box. This is I'll show you what uniform looks like. Now let's do a larger sample size. That's uniform. It's kind of just like a rectangle, like a flat box. Okay, so the shape of the sampling distribution of test statistic is what? Okay, so recall here that one of our assumptions is that the samples come from normally distributed populations, or I should say that the sample means are approximately normal. Okay, in this example, we have 35 observations in each sample. Okay, so we have 35 identify as male, and we have 35 who identify as female. The central limit theorem tells us that if our sample size is over 30, we can assume that X bar is approximately normal. So in the first sample, we have 35 male students, 35 is bigger than 30, so we can assume that X bar for the males should be approximately normal. In the second sample, we have 35 students that identify as female, 35 is bigger than 30, so we can assume that X bar for the females is approximately normal. Therefore, the sampling distribution would be approximately normal as well, based off of the central limit theorem for each group. Okay. We must assume both the female and male student populations are both normal in order to create confidence intervals and perform hypothesis tests with this data. This would be, well, okay. This is a tricky one. It's technically false because of the central limit theorem. So the samples themselves can come from normal populations, and that would be one way for us to check off the assumption. The second way around this, though, is if the central limit theorem takes over. So when n is actually greater than 30, we can say that there's enough evidence to assume that X bar is approximately normal. So if we can assume that X bar is approximately normal, then we can still get around this and conduct the tests anyways. So technically the answer to this is false, because as long as we have enough information in the sample, then X bar is approximately normal. And then we can still work through the steps of the test. But the best thing would be if each of the populations was normal. Okay. So this is actually kind of a good first couple questions, because we're hitting on a lot of the background points of the hypothesis testing procedures and the confidence interval procedures. Sorry, I keep scrolling up and down there. Does anyone have any questions at this point as we work through those two materials? Okay, calculate descriptive statistics, sample sizes, means, and standard deviations for the hours of homework performed by the female and male students. Okay, so in Rcmdr, we will go statistics, summaries, active data sets, numerical summaries. Okay, we will select these two variables, which are the hours for the females and the hours for the males. We're going to ask for the mean, the standard deviation, and do we need to select sample size? Doesn't look like it. We'll click apply. Okay, and here is the output for that. All right. Okay, part D, calculate the ratio of the largest standard deviation to the smallest standard deviation for these two groups. Are the standard deviations for the two histograms of sample data close enough to consider using a pool of variance when creating confidence intervals and performing hypothesis tests for the means of this set of data? Okay, first off, background here. Now, for some lectures, you're going to learn about two independent two sample tests: the pooled procedure and Welch's procedure, or the non-pooled test, if you will. In other situations, you're only going to learn about the non-pooled test. So technically speaking, there are two ways to perform an independent two sample t-test. Okay. So we have the pooled procedure, and two, we have the non-pooled or Welch's procedure. Now, the reason that some of us don't teach the pooled procedure is because the non-pooled procedure is a more conservative test. So always conducting the non-pooled will generally give you a more conservative conclusion. One of the reasons why you will be taught the pooled procedure is because the pooled procedure leads very naturally into the ANOVA situation. But I think it's fair to argue that whether you teach the pooled variance equation now or with the ANOVA is somewhat, it doesn't really matter, because learning how to use that equation, whether you do it up front or with the ANOVA, it doesn't really make a difference. And if anything, for students at the first year level, teaching the pooled variance equation with ANOVA might actually be better, in my opinion, because they can associate that formula with the ANOVA rather than having to differentiate between three different types of two sample hypothesis tests. So I feel that in my experience, it's been a little bit better to teach one way of doing an independent 2-sample test, one way of doing a paired test at this level, because there's already, students already tend to struggle quite a bit with differentiating between all the different tests and all the different assumptions of the test and when to use what anyways. So adding to that, it just doesn't really seem necessary at this point. But later on, if you progress in statistics and you keep taking courses, then you'll start to hear more about the differentiating between these. And at that point, with the background, it'll be a little bit easier for you to do that. So in the lab, to accommodate all of the different lecture styles, we have to talk about both procedures. So you will get a little bit of that pooled flavor here, but the type of procedure you use will depend on your lecturer. Okay, so there's two different independent 2-sample tests, the pooled and the non-pooled. The way that we check to see if you use pooled versus non-pooled is by what is called the rule of 2. Okay, so use pooled procedure if ratio of largest to smallest standard deviation is less than 2. Otherwise, use non-pooled procedure. Okay, so here we have so the ratio of largest to smallest standard deviation equals largest standard deviation divided by smallest standard deviation, which is equal to 1.275088 divided by 1.116530. Okay, so if we type this into R, what we end up with is 1.41201. .41 or 1.14. Okay. So since ratio is less than 2, use the pooled procedure. So this would be an illustration of when we could use the pooled procedure. So basically to determine when we use that, we take the standard deviations and we check to see if the largest divided by the smallest is less than 2. If it is, then we would say use the pooled procedure. So it's almost like an extra check on the test. Okay, so calculate a 95% confidence interval for the difference in the means between the number of hours of homework per class, or the number of hours of homework per classroom hour that female identifying students conduct, or versus male identifying students. Okay, so let's construct that confidence interval. So to do that, we go back to Rcmdr. We go statistics, we go means, and we go independent samples t-test. Okay, so to do a 2-sample t-test, statistics, means, independent sample t-test. You'll notice below here we have the paired t-test. That's what we're going to see an example of when we talk about dependent data. So we select independent samples t-test. The first group here is going to be okay. Oh, that's cool. So the groups are defined by the gender. So here we have groups, and then we select HH per classroom hour. So the actual Rcmdr asks us for the entire variable, and then it splits it by the group. So that's kind of cool. Okay, so we have HH per classroom hour, gender. If we go into options, okay, so we're testing to see if there's a difference. So our alternative is 2-sided. The confidence level, we're constructing a 2-sided hypothesis or a 95% confidence level. So we have 0.95 here. And then assume equal variances. So in this case, we would say yes. So the pooled variance procedure means assume equal variance. So we select yes in the box here. So again, this is found by going statistics, means, independent samples t-test. We separate by gender. Our variable are the classroom hours. Two-sided test, we're doing a confidence interval, so you can just leave this part alone. We have a 95% confidence interval, and we assume equal variance because of the rule of 2. Had we had a ratio that was outside of 2, or we were told just to do a Welch's test, we would just leave this as no. Click OK, and then here is our 2 sample test information, which we can paste in below. Okay, so there's a few questions that are associated with this test. First off, the confidence interval you can see is shown right here. So this is our 95% confidence interval for the data. The test statistic value is shown here for the hypothesis test. We have the degrees of freedom given here and our p-value given here. The alternative, you can see that basically this output is exactly the same as it was in the 1 sample case. Okay. In the question, it asks us to compute the interval. So that's this part below. And then it says, is there evidence that there is a difference in the average homework hours per classroom for the 2 groups? Verify that you can obtain the following output, why or why not. Answer by filling in the blank. Okay, so the questions that are associated with this particular confidence interval are found in this little blurb below. So we have a 95% confidence interval for the average difference in homework hours per classroom hour between female and male students is between 0.05 and 1.195 hours. Okay. So this is the first part. We are 95% confident that the interval contains the true population mean difference in hours of homework per classroom hour on average for male and female students. At B, so we would have 5% significance level here because we constructed a 95% interval. Since 0 is not contained or is not in the confidence interval, there is sufficient evidence to suggest, or I'm sorry, I guess they just want the word is there. Yeah, they just want the word is. So since 0 is not in the confidence interval, there is significant evidence that there's a difference of hours of homework per classroom hour on average for male and female students. Okay, so let's just go over that. We constructed the confidence interval and we found that the difference in average homework hours per classroom hour between the male and female students is between 0.051 and 1.195. So this confidence interval does not contain 0. So because the interval does not contain 0, this implies that there actually is a difference between the 2 groups. So this implies that that male students do a different average amount of homework than female identifying students. Okay. So because the interval is 2-sided and because it does not include 0, we can then say that at the 5% significance level, there is evidence of a significant difference. Right. Okay, in part F, we're asked to calculate a 95% confidence interval for the true mean difference of the same groups, but using the unpooled or non-pooled variance procedure. And then we're asked to answer the exact same question. So basically, let's see if this makes a difference in terms of the conclusions that we reached above. So to construct this test, we'll go statistics, means, independent sample t-test, gender, HH per classroom hour. And then here, we're going to click no. So the non-pooled or unpooled procedure means not equal variance. And we click OK. All right, so that gives us the following. So you'll see here, we have Welch's 2 sample test. All right, so we come back. Let's give this the same color that we had above. Okay. All right, so same idea as before. A 95% CI for the average difference in hours of homework per classroom hour, females and male single parent sole wagers. Oh. Okay, is between 0.051 and 1.194. All right, we are 95% confident that the interval contains the true population mean difference in hours of homework per classroom hour on average for male and female identifying students. At the 5% significance level, there, since 0 is not in the confidence interval, there is sufficient evidence, there is significant evidence that there is a difference, in the hours of homework per classroom hour on average for male and female identifying students. Okay, so if we compare the Welch's procedure, which is the non-pooled procedure, and the pooled procedure, we can see that the intervals are effectively identical in this case. They actually give the exact same output. The big difference here that we can observe, actually, if we compare the output, is the degrees of freedom is slightly different. So you'll see here for the Welch's, you have 66.8. Notice that the degrees of freedom for the Welch's procedure is not a whole number. This is because to compute degrees of freedom for the Welch's, which is the non-pooled procedure, the formula that is utilized here can return decimal placed values. And because we're using computer software, we can still find the p-value to any given degrees of freedom, given the approximations that the system has built in. If we were using the table, we would have to round down to 66 degrees of freedom in order to use the table. So in lecture, typically what we do is we just teach to take the minimum of the sample size -1 as the degrees of freedom, because that will be the most conservative estimate. All right, if we compare the test statistics, we can see they are identical. The confidence intervals are identical. So this really implies that, as you can see, either procedure is going to give the same answer. And in that case, we have a lot of confidence in the decisions that we're making based off the interval. Okay. Okay, use software output to perform a hypothesis test to test the 5% significance level, whether on average, the homework hours performed per classroom hour by male and female identifying students in STAT 151 at McEwen differs. Use the difference with a pool procedure, verify you can obtain the following output. Okay, so we've actually already done this. So we can just pull from here the following information. So this would be our pool procedure. Now we can verify this fairly easily. All right, so in order to get this output, we would go back to Rcmdr. This is going to be the same thing. So statistics, means, independent sample. So we select the gender that we want to split by. We select the variable. We collect options. So we're conducting a two-sided test because we have written below here that we want to test if there's a difference between the two. So we just want to know if male and female averages differ. So that's our two-sided test. The confidence level is 0.95 because we're testing at the 5% significance level. And we're going to assume equal variances for the first part. So we just check yes here for assume equal variance. And you can see that this output is exactly the same output that we had for the confidence interval. Okay. All right. So based off the output, we're then asked to construct our tests. So here we're going to have insert, advanced symbol. We got to pull all these mu's out now. Okay. So we have mu subscript 1 minus equals 0. And then we're testing for a difference. So then the alternative would just be that they are not equal to 0. Okay. All right, so the test stat for this test is given in the output. That's the 2.1742. The degrees of freedom is given in the output, which is 68. Okay, the p-value is 0.03318. So the p-value statement is going to be pt greater than 2.1742 plus p t less than negative 2.1742. And then in this case, we're going to have the p-value, as it's given in the output, is going to be equal to 0.033. Okay, and now we can reject H naught. And the reason we can reject is because the p-value is less than alpha. So we have 0.033, which is less than 0.05. And then we can say at the 5% significance level, there is significant evidence that on average, the homework hours performed per classroom hour by male and female identifying students in Stat 151 at McEwen differs. All right. Are there any questions about any of this? Hopefully you guys are following along. Okay, in part H, we're doing the exact same thing, but we're just using the non-pooled procedure, right? So it says here, basically perform at the 5% significance level the test of difference with the unpooled procedure. So in Rcmdr, we would go statistics, means, independent sample means. We would select our splitting variable, which is gender. We would select our variable of interest, which is HH per classroom hour. And then in options, we would click assume unequal variance. We're still testing at the 5% level. So here in our confidence level, we have 0.095. All right, so we click OK. This is the same output that we had for the interval given above. So we can just paste that down here. All right, and now we can write up some of the conclusions about this based off of what we have. Okay, so here the hypotheses for this test are going to be exactly the same. Our test statistic is again 2.1742. Our degrees of freedom is now 66.835. The p-value statement is going to be exactly the same as it was above. So we have the p-value here being equal to 0.0033. Sorry, 0.0033. The p-value statement will be t greater than 2.17442 plus pt less than negative 2.1742. Again, we will reject H0 for the same reason as discussed above. So because the p-value is less than alpha, we can reject. And then we can say at the 5% significance level, there is significant evidence that on average, the homework hours performed per classroom hour by male and female identifying students in Stat 151 at McEwen differs. Okay. In part I, we have, what are your degrees of freedom with the two independent sample pooled variance t-test? What are your degrees of freedom with the two independent sample unpooled t-test? Are they the same? Why or why not? Okay, for the pooled procedure, our degrees of freedom is 68. For the unpooled procedure, our degrees of freedom is 66.835. Discuss. These two degrees of freedom are different because the pooled procedure uses the formula N1 plus N2 minus 2 to compute degrees of freedom. Whereas the unpooled procedure uses an approximation based off the Welch's test, which takes the ratio of the standard deviations in each group. Hence, it can return a value that has decimal places of accuracy. Okay, so I don't remember off the top of my head exactly what the formula is for the Welch's test. I know that it's quite complicated and we don't typically ask students to use it. In Rcmdr, because we have computer software, computing this is not an issue. So the t-test procedures that are in this system can compute this degrees of freedom very easily. So the reason why you have 66.835 is because the formula that is being used to compute the degrees of freedom for this test takes into account the standard deviations, and hence it can be a non-whole number answer. Whereas with the pooled test, the degrees of freedom is simply the sample sizes added together minus 2. So in that case, you're just adding two whole numbers together and then subtracting 2, which would give you a whole number. Okay. Okay, use software output to perform a hypothesis test to test at the 5% significance level whether on average the homework hours performed per classroom hour by female identifying students is more than the homework hours performed per classroom hour by male identifying students. Use an unpooled variance procedure, use the difference, fill in the answers below. Okay, so now what we're doing is a one-sided test. So we want to test if the number of hours performed per classroom hour by female identifying students is more than the males. Okay, so what we're going to have here is statistics, means, independent sample mean. All right, and then we will select in the options difference greater than 0. So notice above here that Rcmdr is telling us the difference is F minus M. So Rcmdr is telling us that the differences are being taken as female average minus male average. We want to know if females do more homework on average than males. If females do more homework on average than males, that would mean that the female average is bigger than the male average, which would mean that the difference is greater than 0. So in this case, we're doing an upper tailed test. So we select upper tailed test here. And we are assuming unequal variance because the question said to use the non-pooled procedure. And we have a 5% significance level. So we select alpha, or confidence level in this case would be 0.95 since alpha is 0.05. We click OK. Here's our output. All right. Okay, so now we can answer some of the general questions that we usually have about these tests. Okay, so first off, the hypotheses. Okay, so let's write it slightly differently this time. So we'll go mu female and mu male. So we're going to have that mu female minus mu male is equal to 0 versus the alternative that mu female minus mu male is greater than 0. So we expect this difference to be positive if females are doing more work on average. Okay. All right, so the test statistic you'll see here is exactly the same as it was for the 2-sample test. Okay. The degrees of freedom is exactly the same as it was for the 2-sample test. Now the p-value statement is going to be slightly different because we're considering only a directional test. So we're only going to have p greater than 2.1742. And then you'll notice that as a result of this change, the p-value is only 0.01662. Okay. So that's half of the p-value that we had before. So in this case, again, what we'll find is that we reject H naught, so 0.01662, because the p-value is less than alpha, which is 5%. And then we can say at the 5% significance level, there is significant evidence that on average, the homework hours performed per classroom hour is greater for female identifying students than male identifying students. Okay, I will be right back. I have to use the facility really quick. So I'm just going to pause this. Okay, so those are illustrations of the independent 2-sample t-test using either the Welch's procedure, which is the non-pooled procedure, or the pooled procedure, which is the pooled procedure. Now, the other type of test that we need to study in the lab today is the paired test. So an example of the paired test is given a little bit earlier on. So this would be exercise 24, I believe. So oh, there's 122. So it's actually exercise 21. Okay, so we're going to study exercise 21. So let me just make sure. Yep. Okay. So in exercise 21, we're using the math aptitude data. So in Rcmdr, we will go data, import data from Excel file. So this is math app. Click OK. Okay, and then we want math aptitude right here. All right, so now we can view the data. Okay, so here it is. So you'll see this data set has only 8 observations. We have for each observation 2 measurements, before and after. So if we read the description, we have a 2-week remedial program is designed for students who scored less than 50 on a math aptitude test. 9 students were randomly selected, given the remedial course, and then tested again. Here are the results of the test before and after the remedial course. So the idea here is that you have 2 sets of information: score on the test before the course, score on the test after the course. We want to know if the course is effective in helping improve math aptitude or score on this test. Now, because there are 2 scores coming from the same observation, this data emits what is called a paired structure. That is, we cannot assume that the values in before are independent of the values in after. So they are dependent values for each observation. So in order to test if there's a difference in the average score after the test compared to before the test, we construct a row of differences, and then we perform the test on that row of differences. Okay, so here our differences are -6, -17, -18, -4, 5, -2, 4, -12, and 0. So we are going before minus after. So each of the differences here are the before group minus the after group. In part A, it says compute the difference in grade for each student, then find the mean deviation and of the differences. So you can see that these are already given to us, but we should be able to verify them fairly easily using Rcmdr. So if we go back into our Rcmdr and we click statistics, summaries, numerical summaries, and then we select the differences here and we click OK, this will give us the mean and standard deviation of our differences. To compute the differences, we just take the values for the variable. So 47 minus 53, which is -6, 41 minus 58, which is -17, etc. Okay. And the data set already comes loaded with these. Okay, the mean of the differences is the -5.556, and the standard deviation of the differences is 8.487, as given in the output. There, that's a little more clear, I think. It is assumed that the differences in scores follow a normal distribution. Find the 98% confidence interval for the true mean of the differences in grades for students who are given the remedial course and those for students who are given the remedial course, sorry. Okay, so this is going to be fairly straightforward. There's actually two different ways that we can accomplish this. So we can go statistics, means, paired t-test. And then we would select first variable is before, second variable is after. So this would be the first way that we can do it. So the first variable is the variable that's leading the pack, and the second variable is the variable that would be, or is the variable that's being subtracted. So we have before, subtract, after. So first, subtract, second. So we click OK here, and we end up with the following results. Okay, now there's another way that we can do this, which is kind of cheeky. So because when we look at the data set, you can see that in the last column, you have before minus after. So because it's actually a paired sample t-test is actually a one sample t-test, you can go statistics, means, single sample t-test, and you can select directly the before minus after column. And then you'll notice that if we compare these two, it's exactly the same output. So let me see if I can get this all onto one slide for you. Okay, I will just. Right. So you'll notice here, everything is the same because a paired t-test is just a one sample t-test, but it's being conducted on a set of differences directly. So notice that all the output here is the same. Okay, so the interval for this procedure, let me make this even smaller just to try and get everything onto the same slide. Okay, so the interval for this procedure is -12.0791 to 0.0968. It's unfortunate news. Okay, so what does this mean? We are 95% confident that the true mean difference before minus after falls between negative 12.08 and 0.097. Since 0 falls inside the interval, we do have significant evidence that the true mean difference differs from 0. Or sorry, we do not have evidence. Okay, so the interval contains 0 in this case, which means that there is some evidence that the true average score in your grade on this test could be 0, which means that your score didn't change after the course, which sort of implies that the course wasn't effective, at least for these sample of students. Okay, use a hypothesis test. Oh, wait, did this say? Oh, I'm sorry, 98% confidence interval. Okay, so statistics, means, pair t-test, options, 0.98. Okay, and then if we wanted to do the one sample case, sorry about that, means, single sample, 0.98. Right. And then this would be negative 13.7496 to 2.63845. Okay, but same conclusion. Use a hypothesis test to test whether the students perform better on average following the remedial program. Okay, this is a very tricky question. So it's asking us if they performed better following the program. Now, what that would mean is that the average score after the test would be bigger than the average score before, sorry, the average score after the remedial program would be greater than the average score before the remedial program. Our difference is constructed as before minus after. So if the results of the test are actually greater, or if the results of the test show that the program improved the score on the test, we would expect the before program average to be less than the after program average, which means that we would expect this difference to be less than 0. So what we would do here is we would click statistics, means, pair t-test, before, after, and then in the options, we would do difference less than, and the same confidence level 0.98 because it's a 0.02 significance level. Okay. So that gives us our pair t-test results, which is shown here. Okay, and then what we would have below here would be insert advanced symbol, mu d equals 0, mu d less than 0. Okay, our test statistic is t equals negative 1.9638. Our degrees of freedom is 8. Our p-value statement would be pt less than negative 1.9638. And our p-value from the output is 0.0425. Interesting. Okay, so then we would have the p-value 0.0425. which is less than, or sorry, which is greater than our significance level of 0.02. So at the 2% significance level, there is not significant evidence that students perform better on average following the remedial program. Okay, so those are illustrations of how to do the 3 different 2-sample tests that you might learn about in lecture, but most of you will definitely see 2 of them, which are the unpooled procedure and the paired procedure. Again, the structure of the test is exactly the same as the structure that we would have seen in the previous weeks when we talked about confidence interval construction and hypothesis test and the hypothesis test process directly. But in this case, we're just making a slight adaptation to the data because we have 2 samples of information. So in the first case where we have an independent 2 samples, we can do either the pooled procedure or the non-pooled procedure. In Rcmdr, it's a very subtle change. So when you click statistics, means, oh, I need to load my other data set here. So when you click statistics, means independent sample, the option assume equal variance, yes is pooled, no is not pooled. In the second case, when you perform the paired t-test, you have to specify which variable goes first and which variable goes second. So it's first minus second. And that determines the direction of the difference, which does play a big role when we are working on one-sided hypothesis tests. Okay, so I will stop the teaching part here, and I will hang around for the next 10 minutes if anyone has questions and whatnot. Otherwise, I will talk to you guys next week. And yeah, let me know if anything comes up with R or the assignments and whatnot. And yeah, have a good one.